So in this video, we'll continue learning about graphs and all the different information that we can read from them. We're going to start with a brief refresher about the distance formula and the midpoint formula for coordinates in the plane. And then we'll learn about evenness and oddness of functions and different types of symmetry. So, like I said, this should be a little bit of review. We should have seen the distance formula and the midpoint formula before. But we have here the distance between 2 points, x1, y1, and x2, y2 is given by d equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. So let's imagine our coordinate plane. Say we have x-axis and y-axis, and I have any 2 points here in the plane. So I say this one is x1, y1, and this one is x2, y2. If I want to find the distance between them, that would be this straight line distance. Then what the distance formula tells me is that I'll find the distance between their x coordinates. That's x2 minus x1. So that would be represented by this red line here, x2, x1. The distance is this horizontal distance. I'm going to take that distance and I'll square it. Then I want to find the difference between their y coordinates. So in this case, here's y1, here's y2. So that straight line distance is this blue line. I'll take that distance and I'll square it, and then I'll take the square root. So you may be able to tell by the picture on your screen that the distance formula is closely related to the Pythagorean theorem, but all we need to know is what the formula is and how to use it. So the distance between 2 points is going to be the distance between their x coordinates squared plus the distance between their y coordinates squared, and then take the square root of everything. We also have the midpoint formula. So if we're talking about the midpoint, we would mean on this straight line where we found the distance, exactly half the distance between. What if we wanted to know exactly the coordinates of this point? Well, the midpoint should have, for its x coordinate, the average of the 2 x coordinates, and for its y coordinate, the average of the 2 y coordinates. And so that's exactly what the midpoint formula says. It says add the 2 x coordinates and divide by 2, add the 2 y coordinates and divide by 2, and that's going to give you the x and y coordinates of the midpoint. So hence we have these 2 formulas, distance formula and midpoint formula, and we can use them to do a variety of different things. So here's an example. The question tells us to find the perimeter of a triangle with vertices at 0, -2, -6, 6, and -3, -2. So let's draw our coordinate plane, and we'll just put in some hash marks. And we'll just say each of these represents 1 unit. So 1, 2, 3, 4, here's -5 and +5 and +5. Let's plot these points. So we have 0, -2. 0, -2 is here. And we have the point -6, +6. So -6 and 6 should be somewhere up here. Doesn't have to be a perfect drawing. It's just to give us an idea. And -3, -2. That should be right around here. So the problem tells us that we want to form a triangle that has these vertices. So we can draw that in. And we want to find the perimeter of the triangle. So that would be adding up the lengths of the sides of the triangle. Now, how could I find the lengths of the sides? Well, that should be the distance formula. So I'm going to give each side a name. Let's call this one A, B, and C. We want to use the distance formula between the vertices to find each of these distances A, B, and C. So let's start with A. Let's say I want to find A. Well, that would be applying the distance formula to the points -3, -2, and -6, 6. And what I'm going to do is I'm going to make assignments here. We know that we want to call one point x1, y1. So let's say this is x1, y1. And we want to call one point x2, y2. And it doesn't matter which is which. As long as I'm consistent, it doesn't matter which is which. Now, all I do is plug into the formula. So this distance A should be the square root of x2, which is -3, minus x1. So that's -6, and I use parentheses to help me remember to distribute that minus. And then I square it. Then I add y2, which is -2, minus y1, so -6, and I square it. That's going to be the square root of, here I have -3 plus 6, so 3 squared, and -2 minus 6 is -8, -8 squared. And that is the square root of 9 plus 64, which is the square root of 73. And I don't have to simplify that any further. I'll just say A is equal to square root of 73. Very good. Now let's find B. I'm going to repeat the exact same steps, except I'm going to change which points. B is the distance between -6, 6 and 0, -2. So instead of calling this one x2, y2, I'll call this one x2, y2. And repeat the same process of just plugging them into the distance formula. So this becomes square root of x2 minus x1 is 0 minus -6 squared, plus y2 minus y1 is -2 minus 6 squared. So that ends up being square root of 6 squared plus -8 squared. So that's square root of 36 plus 64, which is square root of 100. And in this case, we can easily simplify, that's 10. So side B is length 10. Finally, let's do this one more time for C. When we have C, we're finding the distance between -3, -2, and 0, -2. So in this case, I'm going to keep x2, y2, and change -3, -2 to x1, y1. Okay, so then C, plugging into the formula, is equal to one big square root, and inside I have x2 minus x1, so 0 minus -3, everything squared, plus y2 minus y1 is -2 minus -2, everything squared. So that ends up being the square root of -3 is +3, so 3 squared, plus -2 plus 2, 0 squared. Square root of 3 squared is square root of 9, so that's 3. Okay, so side C has length 3. So now we're ready to say that the perimeter is just adding the three sides, the lengths of the three sides. It's 10 plus 3, that's 13, plus square root of 73. Another type of problem that we might be asked to do is to find the point on the line y equal to x that is equidistant from the points minus 10 minus 8 and 6 minus 7. So we have, if we try to visualize this, we have these points, minus 10 minus 8 and 6 minus 7. So let's say this is minus 10 minus 8, and 6 minus 7. So just a very rough sketch here. I want to find a point on the line y equals x that's equidistant from these points. Now, I know what the line y equals x looks like. Y equals x is the diagonal line of slope 1 that passes through the origin. So we talked about this a little bit when we did parent functions. And we said that any point that's on the line y equals x is going to be something like 1 comma 1 or 2 comma 2, or if it's down here on the other side it might be negative 1 comma negative 1. So that is to say that any point on the line y equals x has the form x comma x. By that I just mean that the y-coordinate is going to be the same number as the x-coordinate, whatever it is. And then we're looking for a point like this, xx, where this distance from 6, negative 7 is exactly the same as this distance from negative 10, negative 8. So how do we find the right point? Well, first of all, let's find out what would the distance be from minus 6 minus 7 to x comma x. We would have, let's say this distance is a and this distance is b. Then we would have a is square root of, let's make the red point xx, let's use it as our x1, y1, and we'll use the blue point 6, negative 7 as our x2, y2. So then applying the distance formula, that would be 6 minus x, everything squared, plus minus 7 minus x, everything squared. That should be the distance a. What if I had the distance b? The distance b, well, that should be minus 10 minus x, everything squared, plus minus 8 minus x, everything squared. And the problem tells me that I want to find an x that will make these two things equal. Equidistant means equal distance, so the distance a equal to the distance b. How do I do that? Well, I'm going to set them equal to each other and try to solve for x. So I'm going to say I want a equal to b. That means I want 6 minus x squared plus minus 7 minus x squared equal to minus 10 minus x squared plus minus 8 minus x squared. Okay, so I think a good first step would probably be to go ahead and square both sides. Now I also know that I can simplify this stuff under the square root, and eventually I'll probably do that. But let me first just square both sides. That's going to get rid of those square roots, and what I'm going to have is 6 minus x squared plus minus 7 minus x squared equal to minus 10 minus x squared plus minus 8 minus x squared. Okay, this is looking good. Now I think I am going to have to expand these squares in order to keep going with the problem. So I'm just going to distribute 6 minus x times 6 minus x. That's going to give me 36 minus 12x plus x squared, then minus 7 minus x times minus 7 minus x. That gives me 49 plus 14x plus x squared. And all of that is equal to, if I expand on the right side, I have 100 plus 20x plus x squared plus 64 plus 16x plus x squared. Okay, now let's combine like terms. I see on both sides I have x squared plus x squared, so I get to say that's 2x squared. Then I have minus 12x and plus 14x, so let's say that's plus 2x. And 36 plus 49, that's going to be plus 85. On the right side, again, I have x squared plus x squared, so 2x squared. I have 20x plus 16x, so that's plus 36x. And 100 plus 64 is plus 164. Now, I want to solve this equation for x, so I want to move everything to one side and set this equal to 0. So let's subtract 2x, 2x squared from both sides. I'm going to subtract 2x from both sides, and I'll subtract 85 from both sides. What does that leave me with? Well, 2x squared minus 2x squared. On the left side, I have 0. Here, this also cancels. I have 36x minus 2x, so 34x. And then I have 164 minus 85. So 164 minus 85, that should be plus 64 minus 80 is 84, minus 5, 79. Okay, then last thing I want to do is solve for x. So let's move 79 over. I get to say this is minus 79 equals 34x. And then x will be equal to minus 79 over 34. But it asked me to find the point xy. All I have so far is the x coordinate of the point. I need a point. And I already know that this point is on the line y equals x. That means the y coordinate is the same. So this is going to be my point. Minus 79 over 34, minus 79 over 34. This point should be of equal distance from this guy. So it looks like it's probably somewhere here. That should have equal distance from both points. Another type of problem we could do would be the midpoint of a line segment AB is at -5, -4. If A is equal to 6, -7, find B. So again, let's draw the picture just to get some idea of what we're talking about. 6, -7 is A. Let's plot that. So 6 and -7. Do a little bit more accurate. It doesn't have to be a perfect sketch, but let's say 6 and -7. So this is A, and the midpoint of the segment AB is -5, -4. So let's roughly plot -5, -4. So this point, -5, -4, is halfway between A and B. So that seems to suggest that B should be somewhere further out here. So B's out there somewhere. Okay, so we want to find a B where the midpoint of the line segment AB, if this is A, should be as given. So B is somewhere on the left side. All right, well, let's use the midpoint formula to try to find it. The midpoint formula tells us that the midpoint of the segment AB, if I call this x1 and y1, and B is x2, y2, then the midpoint should be 6 plus x2 over 2, comma, minus 7 plus y2 over 2. And I know that the midpoint is actually minus 5 minus 4, so what I have are two equations. So this one should be equal to minus 5, and that will help me solve for x2. This one should be equal to minus 4, and that will help me solve for y2. So let's do this. We have 6 plus x2 over 2 equals minus 5. I'm going to multiply both sides by 2 and get 6 plus x2 is equal to minus 10. Then I want to subtract 2 from both sides, so I get that x2 should be minus 16. So far I know the x coordinate of B. I'm going to do a similar process here to find y2. I'm going to say minus 7 plus y2 over 2 is equal to minus 4. I want to multiply both sides by 2, so I get minus 7 plus y2 is minus 8. Then add 7 to both sides, so I get y2 is minus 1. So minus 16 minus 1, as we said, it's somewhere out here, and then that makes sense. I didn't leave myself enough space. It would actually be further out, but it's somewhere over here in the third quadrant. So B is minus 16 and minus 1, because x2 is minus 16 and y2 is minus 1. Okay, so that's a type of problem we can solve with the midpoint formula. So that should have just been a little bit of review of midpoint and distance formula. Now let's introduce a new topic for our class, which is evenness and oddness of functions. So first we have the definition of an even function and the definition of an odd function. The function f is an even function if f of negative x is equal to f of x for all x in the domain. The right side of the equation of an even function does not change if x is replaced by negative x. The function f is an odd function if f of negative x is negative f of x for all f in the domain. Every term on the right side of the equation of an odd function changes its sign if x is replaced by negative x. So the thing that we just have to remember is this definition of even function and this definition of odd function. So if we're asked to check if a function is even or if a function is odd, we're always going to start by plugging in f of negative x and then see whether we get back our original function f of x, or maybe we get back the negative of our original function, negative f of x, or maybe neither thing happens, because not all functions are even or odd. This is a very specialized type of function. And then in a minute we'll discuss the symmetry and what the implications are of being an even function or an odd function. So determine whether each function is even, odd, or neither. I know that the way that I start is always the same. I plug in negative x. So I have minus x cubed plus minus x. Everywhere that I had x, I replace it by negative x. I simplify, and what I want to find out is, do I have minus f of x in the end? Then I'll call the function odd. Do I get back the original function f of x in the end? Then I'll call the function even. If neither one is true, then I say it's neither odd nor even. So here, negative x cubed is like minus x times minus x times minus x. And then we have plus minus x. That's the same thing as just subtracting x. The reason I wanted to write out minus x times minus x times minus x is to remind us, we know that a minus times minus is a plus. So these two minuses cancel, but I have one extra minus. So this does end up staying negative. This is minus x cubed minus x. And then I can see that I could factor out that minus, and I could write this as minus, start my parenthesis, x cubed plus x. So then when I compare with my original function, this is exactly minus f of x. So f is an odd function. Now let's look at g. The first part is always the same. I plug in negative x. So g of negative x is minus x squared plus minus x, which is equal to minus x times minus x. And then adding negative x is the same thing as subtracting x. Now I see that minus times minus is plus, so this just goes back to being positive x squared, and I have minus x. So now if I compare with my original function, I see one of the signs changed. This plus x became minus x, but the x squared stayed x squared. So this is neither. Because in order to be odd, I would need negative x squared, and in order to be even, I would need plus x. Okay, last example. Let's take a look at f of x is x squared minus x to the power 4 plus 1. I start by plugging in minus x. I say this is f of minus x equals minus x squared minus x to the power 4 plus 1. And I know that that's equal to minus x times minus x minus x to the power 4 means I multiply minus x 4 times, and plus 1. So minus times minus is positive. That means this becomes x squared. Here in the middle, again, I have minus times minus is plus, so these become plus. And I have one more pair. I have minus times minus is plus again, so all of these became plus. And I still have this minus out in front. That stays. So this is minus x to the power 4 plus 1. Now I compare with my original function, and I see that that is exactly what I started with, so this is equal to f of x. F of minus x equals f of x tells me that f is an even function. So now we've seen one example of an even function, and the way we checked was we plugged in minus x, and what we got back was the original function. We also have seen one example of an odd function. We plugged in minus x, and what we got was minus f of x. And we've also seen an example that's neither even nor odd, because when we plugged in minus x, we got something different. Okay, now the graph of an even function, remember even means f of minus x equals f of x, is going to be symmetric with respect to the y-axis. And the graph of an odd function, which means f of minus x is minus f of x, is symmetric with respect to the origin. So let's see some examples, and maybe we can clarify these ideas a little bit. Example 4 says, use the graph to determine if the function is even, odd, or neither. Note, if for every point xy there is a corresponding point minus xy on the graph, then it is symmetric about the y-axis, or even. If for every point xy there's a corresponding point minus x minus y, then it is symmetric to the origin, or odd. So let's take a look at our first graph here. And I can see visually that it is symmetric with respect to the y-axis. And what I mean by that is that the image on the left side of the y-axis is a perfect reflection of the image on the right side of the y-axis. So that's just my visual interpretation, but how do I justify this mathematically? Well, let's go back to this note here. It said for every point xy, so for example, maybe I have xy is the point 1, 0. Then I would need to check, is negative 1, 0 also there? And it is. And I should be able to do this with any point. So even if I pick something here, like maybe this is 1/2 and 1/2, I need to check whether negative 1/2 is on the graph. So I would go to negative 1/2, 1/2, and I would see that it is in fact there. And I can do that with every point. So this is even. Now, how does that relate to the idea of f of x, or f of negative x, equal to f of x? Well, it directly relates because it says that the y-coordinate associated with the value x is exactly the same as the y-coordinate associated with the negative version of it. And that's exactly what it means to be symmetric around the y-axis. If I take any x, I find its corresponding y value. Then, if I moved the same number of units away from the origin in the opposite direction, I should get the exact same y value. That is symmetry with respect to the y-axis. Perfect. Okay. Now, this next graph is not symmetric with respect to the y-axis. This would be an example of where we would say a function is neither even nor odd. It's pretty close to the first picture that we looked at, except for this point, negative 1, 0, doesn't show up here. Instead, we have negative 2, 0. So if I went back to the note and I asked myself, okay, for every xy on the graph, like negative 1, 0 is like positive 1, 0, then do I get negative 1, 0 on the graph? And I would have to say no, I don't, because this point isn't on my graph. So I can right away say it's not even. What about oddness? If I start with the point 1, 0, then negative x, negative y would also be negative 1, 0. And it's just not there, so I say it's neither even nor odd. Okay. The next question asks us to use the graph to determine if the function is even, odd, or neither. So let's look at this first example, and if I want to claim that my graph is even, then I know that for any point xy, let's say this is xy, excuse me, let's say this is xy, then I need to be able to find minus x, y. So the x coordinate here is maybe like minus 2.5, so let's go over to positive 2.5 and see, do I have the point minus xy? I don't. So this is not symmetric with respect to the y-axis, and that's also pretty clear visually. If I want to know if it's odd, I'm looking for symmetry with respect to the origin. That might be a little bit more difficult to see visually, but I can do the same kind of checking. Now for this point xy, my question is, do I get the point minus x minus y? So minus x minus y would have the same x value, but I'd go down here, and I find that that is on my graph. So this is a good sign. And so this graph is actually a pretty good example of what it means to be symmetric with respect to the origin. It means that whatever is going on, say here in my first quadrant, is first reflected across the x-axis and then reflected across the y-axis. Rather, first across the x, then across the y. Or you could go first across the y and then across the x. Okay. So symmetry with respect to the origin is this type of shape that you see here, often kind of an S shape, and the checking that we do is that for any point xy, we can find negative x, negative y on the graph. Now I only checked one point, but we need to be able to do this for every point, and it turns out that we certainly can. So for example, this point corresponds to this point. If this is xy, then this is minus x minus y. And so on. Okay, what about the second graph? So let me just make a note here that this is an odd function we determined. In the second graph, it's definitely not even, because I can see that I don't have symmetry with respect to the y-axis. For example, this point, xy, if I was even, I should be able to find the same y value with the negative x value, negative x comma y, and that's not on my graph. So it's not even, I can tell right away. What about oddness? So then I would need negative x, negative y to be present. So that would be here, and that is on my graph. And I should be able to do this with any point. So if I test this out, then, for example, this point is here, and it is in fact symmetric with respect to the origin. So I can do this with any point, so I say the graph is odd. All right. The third graph, I want to check if I choose a random point, say maybe this one, and I call it xy, then is negative xy on my graph? Yes, it is. And visually, I can also see that if I split this in half down the middle along the y-axis, then the image on the left side is a perfect reflection of the image on the right side, so I get to say even. This fourth graph is also even. Again, just from looking at it, it's symmetric with respect to the y-axis. I could also check that for any point, xy, I can find negative x and y. What about the next graph? Well, the next graph is definitely not even, because I can see that if I reflect this point, it's not showing up. What about oddness? If it were odd, then this point would have to be on the graph down here, and it's not. In fact, it would be even further down. It would be this point. So this point does not show up on my graph, so it's neither even nor odd. And the same thing with the last one here. The last one is neither even nor odd because, again, I can find a point where if I reflect across the y-axis, it's not there, so it's not even. Also, if I reflect across the origin or across the diagonal, it's not there. That would be somewhere here, maybe here, and that point is not on my graph, so it's neither even nor odd. Okay, so we should be able to do this both visually and algebraically. Let's look at another example where we might have to do it algebraically. Our function is 4x squared minus 3 absolute value of x. So first it asks us to find f of negative x and negative f of x. So we know that f of x is 4x squared minus 3 absolute value of x. F of negative x, I just replace x by negative x everywhere in the function. But I know that x squared and negative x squared are the same thing. That's 4x squared. Because negative x times negative x, I have negative, and negative cancels, gives me positive. Also, I know that the absolute value just gives me back the positive part, so absolute value of negative x is just absolute value of x. So f of negative x is 4x squared minus 3 absolute value of x. I also need to find minus f of x. Minus f of x is minus of 4x squared minus 3 absolute value of x. So that's minus 4x squared plus 3 absolute value of x. So these are the three things that it asked me to find: f of x, f of minus x, and minus f of x. Question A says, is f of x equal to f of minus x? And it looks like it is, yes. B, is f of minus x equal to minus f of x? So now I'm comparing these two, and they're different, so no. And then finally, is this function even, odd, or neither? Well, the answer to part A being yes, that tells us that this is even. If B was true, then it would be odd. So we say the function is even. Let's do another one of this type. We have f of x is minus x to the power 8 plus absolute value of 3x. First, I find f of minus x. So f of minus x is minus of minus x to the power 8 plus absolute value of 3 times minus x. And minus x to the power 8, I know that minus times minus is plus. So if I have 8 copies of minus x, then I have 4 pairs. So they all become plus because I have an even number. So this is minus x to the power 8. And this is absolute value of minus 3x, but absolute value of minus 3x is just absolute value of 3x. I also need to find minus f of x. So minus f of x is just minus of minus x to the power 8 plus absolute value of 3x. If I distribute that minus, that becomes positive x to the power 8 and minus absolute value of 3x. Now, the question asks, A, is f of x equal to minus f of x? So I'm going to compare f of x, what we started with f of minus x, and it is equal. I'm going to also compare f of minus x with minus f of x, and I can see that this is not equal. So just like in the previous exercise, that tells me that this function is even. If B was true, then the function would be odd. How about minus 8x to the 5th minus 6x cubed? So let's find let's say first we have f of x equal to minus 8x to the power 5 minus 6x cubed. Let's find f of minus x, plugging in minus x anywhere I have an x, so this is minus x to the power 5 minus 6 times minus x to the power 3. Now, minus x to the power 5 is going to give us two pairs of minuses, so minus times minus is plus, minus times minus is plus, and then I have one minus left over, so this actually is minus x to the power 5. And similarly here, with minus x cubed, two of the minuses will cancel, but I have one minus left over, so minus 6 minus x cubed. So then, if I distribute these minuses, that becomes 8x to the power 5 plus 6x cubed. Now I also need to find f of x and just the negative of that. So that's negative of minus 8x to the 5th minus 6x cubed. And I distribute the minus, and I get 8x to the power 5 plus 6x cubed. So the question asks me, A, is f of negative x equal to f of x? So here was f of negative x. I compare with my original function. No, they're not equal. B, is f of negative x equal to negative f of x? So here's f of negative x, here's negative f of x. And actually, yes, these are equal. So is the function even, odd, or neither? We say odd. We already know that if A was true, the function would be even, but it's not. B is true, so the function is odd. And we've seen in previous examples that we can oftentimes have function where neither are true. It's neither even nor odd, then we would have neither of those things were true. All right. We have one more topic we want to talk about. We've already talked a little bit about how to find x-intercepts and y-intercepts, and we just want to practice one more time using the function notation. So it says, given a function defined by y equal to f of x, the x-intercepts are the real solutions to the equations f of x equals 0. So we already know that if we have some function, maybe it looks like this, then wherever it crosses the x-axis is going to be an x-intercept. In terms of algebra, that is setting the equation equal to 0 and finding all of the x values where the equation is 0. On the other hand, the y-intercept is where the function crosses the y-axis, and in terms of the function notation, that just means plugging in x equal to 0 and seeing what is the function value at that point. So graphically, we should be able to look at a picture and see the x and y intercepts. So I'm going to use red for x-intercepts and black for y-intercepts. And let's just find them. And remember, when we're talking about intercepts, we are talking about the point. So we would, if we needed to list them, we would actually want to list the ordered pairs, x and y. So any place that the graph crosses the x-axis, that means that the y-coordinate is 0, then that's an x-intercept. And you can see that this graph actually has a lot of x-intercepts. And it looks like the graph probably keeps following this pattern to the left and to the right, so it has potentially infinitely many x-intercepts. And what about y-intercepts? Well, because this graph was odd, I know that it passes through the point 0, 0. That makes 0, 0 is both an x and a y-intercept. Okay, very good. Similarly, we remember that we found out that this next graph was also odd. So it has an x-intercept here, an x-intercept here, and an x-intercept at the origin. This is also the y-intercept. So that's going to be true on these graphs where the function is odd. Now what about the third graph? The third graph we've seen before, and we said it was an even function. Let's find its x-intercepts. Well, it crosses the x-axis here, and here, and here, and here, and here, and here, and just like the first graph, it looks like it keeps going in this pattern, so probably it crosses the x-axis many other places. And where does it cross the y-axis? Just here. So we know that the x-intercepts are going to be ordered pairs where the y-coordinate is 0. The y-intercept is going to be an ordered pair where the x-coordinate is 0. Since this graph was even, these x-intercepts are going to be symmetric with respect to the y-axis as well. But it doesn't have this property that the origin is both an x-intercept and a y-intercept. Okay. Now, the fourth graph here, we have a y-intercept where the graph crosses the y-axis. And the graph is symmetric with respect to the y-axis. Clearly, it was an even function. But if we look, we actually don't find any x-intercepts at all. And that's perfectly okay. That means, in terms of our function notation, if this is f of x, so let's say this is the graph of f of x, that means that f of x equals 0 has no real solutions. If this is the case, that f of x equals 0 has no real solutions, then you'll have a graph which never crosses the x-axis. Okay. Now the last two graphs, we did say that they were not even or odd, but that doesn't mean that they don't have x-intercepts, y-intercepts, or both. And clearly, we can find x-intercepts and y-intercepts. So the graph here has 3 x-intercepts and 1 y-intercept. It was neither even nor odd, but I can tell visually that this is true. Whereas the last graph also has 3 x-intercepts and 1 y-intercept, and it just so happens that the origin is both the x-intercept and the y-intercept. But that doesn't mean that this graph was odd. Remember, this graph was neither even nor odd. So if we compare back to the first two graphs, what this tells us is that if it's odd, then it's going to have passed through the origin, and therefore the origin is both an x-intercept and a y-intercept. If the graph is continuous here. But just because that's true, just because it passes through the origin, then that doesn't make it odd. So any graph that passes through the origin is going to have 0, 0, both an x-intercept and a y-intercept. Okay. That does appear to be our last exercise. So we'll stop recording here and do more in the next lecture.